Welcome to an exploration of one of the most exciting frontiers in energy technology. Today, we're diving into the world of quantum batteries, a revolutionary approach to energy storage that could transform how we power everything from smartphones to electric vehicles. Unlike traditional batteries that rely on chemical reactions, quantum batteries harness the mind-bending principles of quantum mechanics, promising exponentially faster charging times, greater energy density, and potentially longer lifespans. Join us as we uncover how this technology works, the breakthroughs happening in labs around the world, and the profound implications for our energy-hungry future. Traditional batteries have served us well for centuries, but they operate on principles that fundamentally limit their performance. These conventional power sources rely on chemical reactions to store and release energy, a process that's inherently sequential and bound by the laws of classical physics. Quantum batteries, however, operate in an entirely different realm. These cutting-edge energy storage devices harness the principles of quantum mechanics to store energy in quantum systems such as atoms, molecules, and specially engineered quantum materials. Recent research published in Nature Communications has demonstrated a groundbreaking advancement, a quantum battery prototype that can theoretically charge exponentially faster than the lithium-ion batteries we use today. This isn't just an incremental improvement, it represents a fundamental paradigm shift in energy storage technology. The remarkable advantage of quantum batteries lies in the phenomenon physicists call quantum entanglement. This is one of the most fascinating and counterintuitive aspects of quantum mechanics, where particles become connected in such a way that their quantum states cannot be independently described. Even when separated by vast distances, these entangled particles instantaneously affect one another, what Einstein famously called spooky action at a distance. In quantum batteries, this property enables what researchers term collective charging, where all the quantum cells in a battery can be charged simultaneously rather than sequentially. Think of it like filling a traditional battery one cell at a time versus filling all cells at once. This collective behavior allows quantum batteries to bypass the time limitations that constrain conventional batteries, potentially reducing charging times from hours to mere seconds. This represents not just a technical improvement, but a complete reconceptualization of how we think about energy storage and transfer. The field of quantum batteries is rapidly moving from theoretical possibility to experimental reality. A team at the University of Adelaide in Australia, led by Dr. James Kwok, recently achieved a significant milestone with their proof-of-concept quantum battery. Their innovative approach used spin systems in diamond nitrogen vacancy centers, essentially, atomic-scale defects in diamond that can be manipulated at the quantum level. What makes their experiment so remarkable is that they demonstrated a quadratic decrease in charging time as the number of quantum cells increased. This relationship between charging speed and system size is simply impossible in classical systems and provides tangible evidence of the quantum advantage in energy storage. Meanwhile, across the globe at the Center for Theoretical Physics of Complex Systems in South Korea, another team has developed a quantum battery model using superconducting qubits. Their system demonstrated an astounding 80% reduction in charging time compared to conventional batteries of similar capacity. The South Korean approach leverages quantum coherence, the ability of quantum systems to exist in multiple states simultaneously, creating energy transfer pathways that simply don't exist in conventional battery chemistry. These experimental demonstrations follow theoretical work published in 2019 by researchers at the Institute of Photonic Sciences in Barcelona, who first proposed that quantum entanglement could enable ultra-fast charging. The rapid progression from theoretical proposals to working demonstrations within just a few years highlights the accelerating pace of quantum technology development. The remarkable progress in quantum battery research hasn't happened in isolation. It's been significantly accelerated by parallel developments in quantum computing research. These two fields share many theoretical foundations and practical challenges, creating a symbiotic relationship that has benefited both areas. Quantum computing research has provided both the theoretical frameworks and practical tools necessary for manipulating quantum systems with unprecedented precision. The ability to control individual quantum states, maintain quantum coherence, and measure quantum effects, all essential for quantum computing, has directly translated to advances in quantum battery development. Recent work at MIT has further expanded the potential of quantum batteries by exploring how topological protection could create exceptionally stable energy storage systems. Topological protection is a quantum mechanical property that shields certain states from environmental disturbances, like having a built-in error correction system. This approach could address one of the most significant challenges in quantum technologies: maintaining delicate quantum states in real-world conditions where temperature fluctuations, electromagnetic interference, and other environmental factors can easily disrupt quantum coherence. While quantum batteries remain largely theoretical and experimental today, their potential applications are vast and could transform how we interact with technology in our daily lives. Perhaps the most immediate and relatable application would be in small electronic devices where rapid charging is highly desirable. Imagine smartphones that charge completely in seconds rather than hours, a capability that could become reality within a decade. This would fundamentally change how we interact with our devices, potentially eliminating the anxiety associated with battery life, that familiar panic when you're down to 10% with no charger in sight. It could also change the design parameters for mobile technology. Devices could be engineered differently if designers knew that users could quickly recharge at any time, potentially allowing for more power-hungry features that enhance the user experience. The psychological impact shouldn't be underestimated either. Our relationship with technology would shift if the constant concern about battery life were removed, creating a more seamless integration of devices into our daily routines. Moving beyond personal electronics, quantum batteries could address one of the most significant barriers to widespread electric vehicle adoption: charging time. Current estimates suggest that quantum batteries could reduce EV charging times from hours to minutes, potentially allowing an electric vehicle to recharge in roughly the same time it takes to fill a conventional gas tank. This would eliminate one of the last practical advantages of internal combustion engines and could dramatically accelerate the transition to sustainable transportation systems. Fast-charging EVs would make long-distance travel more convenient, reduce the need for extensive charging infrastructure, and alleviate range anxiety, the fear of running out of power before reaching a charging station. The environmental impact would be substantial, significantly reducing carbon emissions from the transportation sector, which currently accounts for a large percentage of global greenhouse gas emissions. Quantum battery-powered electric vehicles could be the tipping point that makes sustainable transportation the obvious choice for consumers worldwide. Quantum batteries may also prove crucial for stabilizing renewable energy grids, one of the greatest challenges in our transition to sustainable energy. The intermittent nature of wind and solar power creates significant challenges for grid management, as energy production doesn't always align with demand. Quantum batteries could provide an ideal solution due to their theoretically instantaneous response time, making them perfect for absorbing sudden surges in wind or solar power generation and helping to balance supply and demand in real time. Their potential for high energy density could also make grid-scale storage more space-efficient than current solutions like pumped hydro or conventional battery arrays. Grid-scale energy storage represents one of the most significant challenges in transitioning to renewable energy sources, and quantum batteries could provide a solution that conventional technologies cannot match in terms of response time and efficiency. This capability could be the missing piece that enables 100% renewable energy grids, eliminating the need for fossil fuel peaker plants that currently provide backup when renewable sources aren't producing enough power. In the field of medicine, quantum batteries could power implantable devices with significantly longer lifespans than current technologies allow. Pacemakers, neural implants, and drug delivery systems could benefit from energy storage that is both more compact and longer-lasting, reducing the need for invasive replacement procedures and expanding the capabilities of medical technology. Imagine neural implants that could help restore mobility or sensory function without requiring regular surgeries to replace depleted power sources. Or consider implantable drug delivery systems that could precisely administer medications for years without needing replacement. The medical implications extend beyond just longer battery life. The compact nature of quantum energy storage could allow for smaller implantable devices that are less intrusive and more comfortable for patients. This could open new frontiers in personalized medicine and dramatically improve quality of life for those dependent on implantable medical technology. Despite the promising advances, significant challenges remain before quantum batteries become commercially viable. The most pressing issue is scalability. Current quantum systems operate at the microscopic level, and scaling them up to practical sizes presents enormous engineering challenges. The quantum effects that enable the advantages of these batteries are typically observable only at tiny scales, and maintaining these effects in larger systems requires sophisticated engineering approaches that are still being developed. Temperature constraints also pose a significant hurdle. Many quantum systems require extremely low temperatures to maintain quantum coherence, often near absolute zero, -273.15 degrees Celsius. Creating quantum batteries that can operate at room temperature remains a significant research focus. Some promising approaches involve using topological materials or specific quantum states that are naturally more resistant to thermal disruption, but considerable work remains before these approaches can be implemented in practical devices. Additionally, quantum states are notoriously fragile and susceptible to decoherence, the loss of quantum properties due to environmental interaction. Developing quantum batteries robust enough for everyday use will require significant advances in quantum error correction and material science. Research into quantum error correction methods, initially designed for quantum computing, may provide pathways to creating more robust quantum batteries capable of maintaining their quantum advantages in real-world conditions. The manufacturing processes for quantum materials present another layer of challenges on the path to commercialization. Many materials being explored for quantum batteries require exact fabrication techniques that are currently expensive and difficult to scale. Creating the precise atomic structures needed for quantum effects often requires techniques like molecular beam epitaxy, which allows for the deposition of single atomic layers but is extremely slow and costly. Transitioning from laboratory demonstrations to mass production will require substantial investments in manufacturing technology and process development. Companies will need to develop new fabrication methods that can maintain the quantum properties of materials while dramatically increasing production rates and reducing costs. This manufacturing challenge is similar to what the semiconductor industry faced in its early days, suggesting that with sufficient investment and innovation, these hurdles can eventually be overcome. The good news is that major research institutions and companies like IBM, Google, and several energy startups are investing heavily in the technology. Their resources and expertise could accelerate the development of practical manufacturing approaches, potentially bringing quantum batteries to market faster than might otherwise be expected. The development of quantum batteries exemplifies how the convergence of quantum physics, materials science, and energy technology is creating unprecedented opportunities for innovation. What began as theoretical explorations of quantum mechanics is now evolving into a technology with the potential to address some of our most pressing energy challenges. This interdisciplinary approach brings together experts from diverse fields, theoretical physicists developing the mathematical models, materials scientists creating and characterizing new quantum materials, and engineers designing practical systems that can harness quantum effects. The field also draws on advances in nanotechnology, superconductivity research, and quantum information science. This convergence of disciplines creates a fertile ground for breakthrough innovations that wouldn't be possible within the confines of a single field. As research continues and more resources are directed toward this interdisciplinary space, we can expect to see increasingly sophisticated prototypes and eventually commercial applications that leverage the strange and powerful properties of the quantum world to revolutionize energy storage. While commercial quantum batteries may still be years away, the pace of advancement suggests that we are witnessing the early stages of what could become one of the most significant technological revolutions of the 21st century. The journey from laboratory curiosity to commercial product follows a pattern we've seen with other transformative technologies. Current estimates suggest that specialized applications in high-value niches might emerge within 5 to 7 years, with consumer applications following in the 7 to 15-year timeframe, depending on how quickly the engineering challenges can be overcome. The first commercial applications will likely appear in areas where the performance advantages justify higher costs, perhaps in military applications, aerospace, or specialized scientific equipment. As manufacturing techniques improve and costs decrease, we'll see the technology spread to consumer electronics, electric vehicles, and eventually grid-scale storage. This progression mirrors what we've seen with technologies like solar panels, which were initially limited to specialized applications like satellites before becoming affordable enough for widespread adoption. With major technology companies and energy startups investing in quantum battery research, the timeline could accelerate if breakthroughs in manufacturing or materials science remove key bottlenecks in the development process. The development of quantum batteries represents a revolution powered by the fundamental principles of quantum mechanics, a revolution that could be as significant for energy technology as the transition from vacuum tubes to transistors was for computing. Just as transistors enabled the miniaturization and exponential growth in computing power that led to our digital world, quantum batteries could enable an entirely new energy paradigm with capabilities beyond what we can achieve with classical technologies. The implications extend far beyond just faster charging or higher energy density. Quantum batteries could change our relationship with energy itself, making it more abundant, accessible, and sustainable. They could enable new categories of devices that aren't feasible with current energy storage limitations and contribute significantly to addressing climate change by facilitating the transition to renewable energy. As with any revolutionary technology, it's likely that some of the most important applications haven't even been conceived yet. When energy storage constraints that have existed since the invention of the battery are suddenly removed, innovators will find ways to use that new capability that we can't currently imagine. We are standing at the beginning of a new chapter in energy technology, one where the strange and counterintuitive properties of quantum mechanics become tools for solving some of humanity's most pressing challenges. As we've explored throughout this journey, quantum batteries represent far more than just an incremental improvement in energy storage technology. They embody a fundamental paradigm shift that could transform our relationship with energy. By harnessing the principles of quantum mechanics, entanglement, coherence, and collective behavior, these revolutionary devices promise charging speeds, energy densities, and lifespans that defy classical limitations. From smartphones that charge in seconds to electric vehicles that refuel as quickly as gasoline cars, from stabilizing renewable energy grids to powering life-changing medical implants, the applications span virtually every sector of our technology-dependent society. While significant challenges remain in scalability, temperature requirements, quantum coherence maintenance, and manufacturing processes, the rapid progress from theoretical proposals to working prototypes suggests these hurdles are not insurmountable. The convergence of quantum physics, material science, and energy technology has created a perfect storm of innovation, with research accelerating across the globe. As we stand at the threshold of this quantum revolution in energy storage, one thing becomes clear: the strange and counterintuitive properties of the quantum realm may hold the key to solving some of our most pressing energy challenges. The quantum battery represents not just a new technology, but a new way of thinking about energy itself, one that could power us sustainably into the future and fundamentally change how we interact with the technology that increasingly defines our world. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.